each hurt makes my love stronger than before. Ain't that peculiar? A peculiarity.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So when we talk about quantum mechanics, fundamental equations or principles were developed. And so we just talked about the de Broglie's wave equation, and now we'll talk about Heisenberg's indeterminacy equation, also known as the Heisenberg's uncertainty principle. So before I delve into this equation, let me try to talk about it for you to better understand it. So at an atomic scale, the measurement process influences outcome. What does that mean? Light scattered from a baseball measures both momentum and position. However, light scattered from an electron will affect the electron's momentum and position. So again, we're talking about the macro scale versus the nanoscale, where we're talking about electrons, things that are much smaller with a much faster velocity. So in this diagram, I'm showing that if you have an incident photon coming in, you have a new path and velocity for this electron where it's going to get pushed out from its original path. At this point, you can't know simultaneously the position that this electron will take on as well as its momentum. And so that's what this is quantitatively showing, where delta P is the uncertainty in the momentum, delta X is the uncertainty in the position, and that's greater than or equal to Planck's constant over 4 pi. So basically there's a limit on the accuracy to which the momentum and position of a particle can be known simultaneously. And so we can look at this from an incorrect model point of view, which will show why this theory was developed. So in the incorrect atomic model, an electron is located inside the nucleus of an atom. For a hydrogen atom, the electron is then confined in the nuclear diameter of 1.7 times 10 to the power of negative 15 meters, which could be the uncertainty in position of that electron. So now using this formula, we can solve for the uncertainty in the momentum. And this is going to be greater than or equal to Planck's constant, 6.63 times 10 to the power of negative 34 kilogram meters squared over second. I'm just rewriting joules second in terms of SI units. And then we have 4 pi, which is 4 times 3.14. And then we have the delta X, which is 1.7 times 10 to the power of negative 15 meters. So from here, we end up with delta P, or the uncertainty in the momentum, is greater than or equal to 3.1 times 10 to the power of 20 kilogram meter per second. Okay, so from here, since momentum can be written as a product of mass and velocity, we can solve for the velocity, where delta V is 3.1 times 10 to the power of 20 kilogram meter per second, divided by the mass of an electron, which is a constant, 9.1 times 10 to the power of negative 31 kilograms. And we end up with a change in the velocity of 3.4 times 10 to the power of 10 meters per second. So this in itself shows that this is an incorrect model, because the uncertainty in the electron's velocity is greater than the speed of light, which is 3.0 times 10 to the 8 meters per second, or c. And that just doesn't make sense. This is an unrealistic number telling us that the electron does not collapse to the nucleus, and basically it's localized at the nucleus. The Heisenberg uncertainty principle is telling us that atoms must be bigger. That is, there's a physical limit to the minimum size that atoms can exist based on physical parameters, such as the mass of the electron and the speed of light. And so now I'll show you what the correct atomic model looks like to show why the Heisenberg's uncertainty equation works in that case. So in the correct atomic model, the electron is not confined to the nucleus, and we now know from experimental observation that the size of an atom is determined by its electrons outside of the nucleus. For a hydrogen atom, the electron is confined to its atomic diameter of 2.5 times 10 to the power of negative 10 meters, which would be the electron's uncertainty in position. From here, we're going to do the same exact calculation that we did before, where we have Planck's constant, 10 to the power of negative 34. I'm going to go through this a little faster since it's the second time. And then we have 4 times pi. And then we have the distance. And we end up with the momentum uncertainty being greater or equal to 2.1 times 10 to the power of negative 25 kilogram meter per second. So again, let's solve for the change in the velocity, which is this value, the uncertainty and the momentum, divided by the mass of an electron, which is 9.1 times 10 to the power of negative 31 kilograms. And we end up with 2.3 times 10 to the power of 5 meters per second. So this is a large number, but at least it's physically possible in comparison to c, or the speed of light. And so this more reasonable number indicates that this is a more stable and realistic atomic model.
Pure as can be.